Hello everyone, welcome back to this video in the trigonometry lecture series. And in this one we're going to start talking about the area of a triangle. So I'm sure we all know the formula for the area of a right triangle, and that is if you have a right triangle whose adjacent sides are a and b, the area is 1/2 of a times b. And a reason for this is that if you take two copies of this right triangle and arrange them like so, where the right angles are here, then this actually forms a rectangle. And the area of a rectangle is base times height, so take half of that and you're left with 1/2 AB. So let's remember how non-right triangles work. So we need the concept of the base and the height for a non-right triangle. And so once you choose one of the sides to be the base, the height is where you drop an altitude from the remaining vertex down to the line that contains the base. So for this for this triangle, this altitude ends up lying right on the base. But for this one with an obtuse angle adjacent to the base, then the altitude actually ends up going outside. But the important part for height is that if you have a line that runs right through the base, then you drop an altitude down to that line, and then that's the height. So it still turns out that it's a simple formula. It's 1/2 of the base times the height. One way I kind of like to think about this is if we imagine having this made out of paper, a bunch of sheets of paper, each getting shorter and shorter and shorter as we get up. Just like we could take this book and kind of slide it. It's like a book of paper, sort of, and we can slide it until it's a right triangle, and then we can apply the right triangle formula. But I'm also going to show you another way to see that, because that's not super convincing. So the first element is, let's remember the area of a parallelogram. So just like triangles, they have a concept of base and height. Base is one of the side lengths, and then the height is the perpendicular, the distance between the opposite sides, the opposite parallel sides. And it's has the same formula as a rectangle, b times h. So why is this? One way to see this is, first we dissect it, we cut it apart. So we cut it right along this line going down to the corner to make some right angles here and a right triangle. Then what we do is we rearrange it, moving the triangle over to there, and we still have our right angles. And then we can glue it back together, and then we have a rectangle whose base is b and whose height is h. So the area of this rectangle is bh. That means that the area of the original parallelogram was bh. So what are we going to do with this? Let's say that we have a triangle with a base b and a height h. So just like for right triangles, we can take two triangles, two copies of the same triangle, and put them together to form a parallelogram. And then the base of that triangle is the base of the parallelogram, and the height of that triangle is the height of the parallelogram. So if the parallelogram you get with two triangles is as area BH, then that means that the area of the triangle is 1/2 BH. So that is why we have this formula 1/2 BH for triangles in general. Okay, so let's apply some trigonometry. So let's work first in general without concrete numbers so that we get a formula. So the question is, let's say we have an angle and we know the two adjacent sides. So it's a side angle side triangle using trigonometry terms. So what is the area of this? So to be able to apply the triangle formula, we need to know what is the height of this triangle. And if we drop this height down like this, as this altitude of the triangle, then we can see that we've got a right triangle inside. And this right triangle, we know A, we know theta, and the question is, what is h? So recall from some of our discussions of right angle trigonometry in this course, that if you take h divided, if you take the opposite side divided by the hypotenuse, then that is the sine of theta. Or in other words, if you take the hypotenuse times the sine of theta, then that gives you h. So I have written that right there. Okay, so we know what h is. And I guess I'll write that sine of theta is equal to h over a. Okay, so, right, so just it's been a little while since we've talked about this. So our exemplary triangle is that if we have a hypotenuse of length 1 and an angle theta, then the height is sine and the base is cosine. So if we scale by a factor of a, then we get same angle, but a for the hypotenuse, because a times 1 is a cosine for the base, and a sine for the height. So I'm simply taking h and equating it with a sine theta, because a already matches up with the hypotenuse. So that is where this formula is coming from. So we know the area of a triangle is 1/2 base times height. The height is a sine theta, so we can plug that in. And then, rearranging a bit to make it look pretty, we've got 1/2 AB sine theta. So that is the formula for a triangle where you know the two side lengths and the angle between them. So it's always good to do some sort of sanity check when you have a formula. So the first sanity check is what happens if theta is very small? Like, what if we make it go towards 0 so that the triangle just kind of collapses and becomes flat? Like if A is this ladder, say, and we let the ladder fall to the ground, what is the area? We'd hope it's 0. So let's see. If theta is 0, then this is 1/2 AB sine of 0. Sine of 0 we know is 0. Anything times 0 is 0, so we get 0. So we get no area for a flat triangle, a degenerate triangle. You might not want to call it a triangle, but it's sort of like, it's what happens at the very limit of the possibilities of values. Well, what if, on the other hand, we consider what if theta becomes a 90-degree angle, pi over 2 in radians, a right angle. So this gives, plugging it in, 1/2 AB sine of pi over 2. Sine of pi over 2 is 1, so it's simply 1/2 AB. And that's exactly the correct formula for a right triangle. And so that's good. Okay, so we've done some sanity checks, and that is the formula. So let's do an example with some concrete numbers. What is the area of this triangle with side lengths 3 and 4 with an angle between them of 55 degrees to 3 decimal places? So we simply plug it into the formula at 1/2 AB sine theta with 4, 3, and 55 degrees, and then calculating it and making sure we use degree mode, which I did. We get 4.915. It's actually 4.9149122, and so on. Okay, so that was that. Let's do another sort of problem. This is, what if we have an area but we want to know what is the side length that gives you that area? So we know 2, we don't know x, but we know that it's a 65-degree angle. And let's say that we know that the area of this triangle is 5 centimeters squared. So what is the side length to 3 decimal places? So the area is 1/2 of the product of the side lengths times the sine of the angle. And we can cancel out the 1/2 and 2, and then divide by the sine of 65 degrees, and then punch that into a calculator. So x is about 5.517 when I plugged it in. Okay, there's one more sort of problem that we can do, and I'll just write this out as we go. So here's our example. What if we have, suppose we've got this triangle with an unknown angle, and these side lengths are both 2, and it has area 10. That might not be possible. Let's say it has area 1. What is theta in radians to 3 places? So we have the area is equal to 1/2 the product of the side lengths times the sine of theta. And then let's simplify this. So we have 2 sine theta. And then we can divide by 2. And now, this is a trigonometric equation. Let's plot a graph to keep track of how this could work. There is sine. This is pi. This is the theta axis. This is the y-axis. And 1/2 would be about here. So notice that there are actually 2 different solutions in this case. So the solutions are here and there. So when is it that sine of theta is 1/2? In radians, well, let's see. So the thing is, we actually can solve this one exactly. So I'm going to change this problem to this, which is what is theta in radians. And so this, remember, is at pi over 6. And then this one would be at 5 pi over 6. So let's say it's theta equals pi over 6 and 5 pi over 6. Because there are 2 different triangles that actually work. If you think about it, there could be, so pi over 6 is about 30 degrees, so we've got this one. And then the other possibility is this very obtuse one. So it seems plausible, at least from these pictures, that they both would have area 1. But indeed, these are the answers. So anyway, so we've talked about triangles, how to find their areas, how to link up trigonometry with them, and we've gone through a few examples. So I'll see you all next time. Bye.